Kia ora. And thanks, Annette, for the invitation. So I'm just going to present you some of our recent advances in soil spectroscopy here in Manaaki Whenua. So very much an end user perspective of spectroscopy. So we're interested. Part of our business is to try to understand the distribution of soil properties in space and in time, and that's really the real tricky bit of the jobs when you're interested in soil geography, is that those attributes vary a lot. They vary across space and they vary also across time. And measuring those properties is a challenge. It's a challenge because they're expensive and they take time. They're expensive because, well, you got to get out there, you got to dig a hole, grab a sample, and then you got to typically bring those samples back to the lab and do some form of wet chemistry to them. And the lab might have a backlog of samples. So not only those samples are expensive to process, they also can take a little bit too much time to someone's liking when they're, for example, mapping soil for a farmer or whatever. As a result, often you are limited by your budget in terms of how many points you can run through a landscape to try to understand how that landscape works. So that's been a sort of natural justification for using spectroscopy, because that's an obvious way to speed up, but also lower down the cost of analysis of soil properties. So we vetted for the last, I think, 12 years in spectroscopy. So starting with visible near infrared. So that's our instrument. It's an ISD field spec. One of the instruments mentioned by the previous speaker is a very classic research grade instrument that's measure reflectance from 350 nanometer, the bottom range of the visible range, up to 2500 nanometers, which is the near infrared. And so we sort of started using that in the lab. So what you can see here is the field spec instrument in the back, connected to a laptop. You can see some soil spectra here. They're fairly flat, and I'll get back to that later. And here you have a contact probe that can measure directly the soils from the lab in contact. So these are soils that are all. So that's how we typically store samples, where when we bring them back to the field, they're just 2 millimeters sieved and air dried soils. So to predict soil properties from spectra, so what I showed in the previous slide is like you can sort of make out those spectra here. They're really flat, unlike spectra collected on vegetation, like Jan showed. We don't have those big, massive peaks, etc. That's not because there's no information. It's very much the opposite. That's because there's so much information and overtones in those spectra. That's because soil is such a complex medium. So to predict soil properties from spectra, we need some form of modeling, typically a PLS model that can handle that large number of dimensions provided by the spectra, and we calibrate that model on a collection of spectra that has the reference measurements we want to supersede. So typically, if you want to measure carbon, you'd have a collection of spectra that have wet chemistry for carbon or liquid measurement attached to them. So it's very much a sort of ongoing work. What we've been doing is to leverage the presence of the National Soil Archive here in Paris North. So that's an archive of about 40,000 individual samples that have been collected from the 1940s up to today, all across New Zealand. So as of today, we have about 12,000 spectra in our little collection. And depending on the soil attribute, of course, there's more or less reference measurement attached to those 12,000 spectra. Carbon and nitrogen are the most important attributes, so that they're measured on a very wide number of samples. It's kind of the big classic in soil chemistry: carbon, nitrogen, pH, clay, silt, sand, which are more like physical properties of soils. Moving on to available water capacity, the AWC, which is a sort of compound of field capacity and permanent wilting point. And you can see that those PLS models, depending on attribute, can work very well. For carbon, for example, we get R square of 0.9, and sometimes they don't. For other properties, they may not work very well at all. For example, silt is always something that's kind of challenging for many reasons to predict for linear spectroscopy. So depending on the attribute you're interested in, you might be able to do a very good job with spectroscopy, or sometimes maybe it's not the best tool. However, I'd also argue that it certainly depends on the attribute. Some attributes like field capacity and permanent faulting point. So these are two parameters that determine how much water a given soil can store. If you take a soil that is nice and clayey and quite deep, it can store a lot of water. If you think about the Canterbury Plains, where you get all this gravel, obviously there's not a lot of water that soil can store. It's a super important parameter if you're irrigator, for example. If you're someone that manages irrigated land, it's a crucial aspect of irrigation management. But it's unfortunately a very, very expensive and time-consuming thing to actually measure in the lab. It takes several days, specialist equipment. It's a complete dog to measure, and it's very expensive. So in this case, being able to calibrate models predicting those two parameters directly from spectroscopy with a very decent accuracy. So of course, not a one-to-one line, but it still gives us that quantitative measurement that can be actioned on. In this case, in this paper, we tried two different methods: the simple PLS, or what we call PLS SVM, where the latent variables from the PLS are leveraged by a machine learning method called SVM. And what we found is that across the different types of soil in New Zealand, so I've put 4 very common types of soil in New Zealand, the performance might differ, and the model sort of does better in specific soil. What was important for us, though, is that in the recent soils, which are the type of soil that often carry irrigated soils or irrigated land, that model is working reasonably well, and that's a result that's been reported in 2019 paper in Scientific Reports. So as I said, today we have a large number of spectra in our library, but that's an iterative exercise. And what we try to do is to keep scanning soils that are going through our wet chemistry lab and increase the representativity of our library. What we've developed as well is in situ spectroscopy. So those instruments, some of them can be operated in the field, where we would sort of scan a soil core before chopping it in sort of 10 centimeter increment and bring that to the lab. So that those reference measurements made on the slices can be used to calibrate a model. In this case, we calibrated a model of soil organic carbon stocks, how much carbon is stored by the soil. And that allowed us to then deploy that model back to the core. So we've made all these different spectra collected at sort of 1 centimeter intervals. They are the little dots on each of those individual sites. And you can see that it sort of shows that high resolution variations of carbon stocks with depth, which is something that's virtually impossible to do using traditional method. You can't really do carbon stocks on 1 centimeter slide. So that's certainly the sort of new things that spectroscopy can open. And again, that's another paper from on EGSS. A second type of spectroscopy we are using in our lab, and it's sort of a more recent development, is mid-infrared spectroscopy. So as the name suggests, it's an instrument that looks at reflectance further down the sort of infrared part of the EM spectra. Now, the reason why mid-infrared spectroscopy is interesting is, if we go back to the theory, so soil, which is a very complex heterogeneous medium, absorbs light at very distinct excitation energies, and most of these features, they're actually located in the mid-infrared, right? What we see in the near-infrared is the overtones, right? A bit like when you look at a rainbow in the sky. Sometimes you can see make out the second rainbow, but that's very dim. So that would be the NIR, while the MIR might be the actual sort of primary rainbow. So in short, in the MIR, the signal is much better and much clearer. That's the instrument. So that's very much a benchtop instrument. You're certainly not bringing that one in the field. And because nothing is ever free in science, you have a much better signal, but sample preparation is a lot more involved. So you have to sort of finely ground the soil samples. So you can't really just take a normal sample prep. You have to grind it a little bit more and to put it in these little plates here. So you can see here at the bottom that little plate that is then fed onto the instrument. However, the results sort of show or reflect the fact that the signal is much better for carbon and nitrogen in particular, and also for clay. The results are certainly much better usually than that with near infrared. So yeah, very interesting to explore those type of technologies as well if more accuracy is needed. One thing I very quickly touched on is that spectroscopy can also be used with other sensors. So one of the challenges we've had is to calculate carbon stocks directly on fresh cores. I've showed a sort of example before, but the sort of next step was to integrate a spectrometer. Which you can see here, with a gamma radiometer, which basically shoots gamma rays across the core to measure bulk density, right? So the spectrometer can predict percent carbon fairly well. But that gives us that yellow instrument, the gamma densimeter, gives us a much better idea of bulk density. So I'll go very briefly on that, but basically it shows that different sensors can sort of collaborate in a way and give us different information. What we showed on a set of cores collected across New Zealand is that rather than looking at bulk density and combining it with the percent carbon, which is that panel here, we much better fuse those two informations as a multidimensional data set and directly predict from the carbon stock from this information. Of course, even for that one, even for that core scanner, we still collect data at regular intervals alongside core. So that's the green dots on this plot. So that allows us to get very high resolution information of carbon stocks down those soil cores, and that opens ways to sort of try to understand what happens in terms of processes on this soil. So if you get that Manganui soil, for example, you can see that at very high value at the bottom probably suggests there's a buried topsoil. So maybe slow processes have been burying in the previous topsoils that then shows on the core.
Just 1 minute to go.
Yep, so that's good because that's just time for us to step back. So about cost and accuracy, as I suggested before, what we found is that it really depends on the application. Yes, MIR will give you better accuracy, but it's also more costly, both in time and dollars, to prepare the soils. So if you don't need a double-digit accuracy, maybe NIR sometimes is enough. I'll just finish with data-related questions. So as you've seen, we've rolled out quite a few papers over the years about those technologies. What we found is that now our next challenge is to make those spectra actionable by all sorts of researchers in our institutes, right? So it's pretty pragmatic view on these tools. Is how do we make that spectra that spectroscopy operational, right? So it's one thing to build models, but to build a pipeline of models that can be automated, for example, is a large task. So what I show now is how we interact with our database. So typically, if we have this big data set called the National Soil Data Repository, which stores everything we know about soils in New Zealand. What we wanted to do is to make sure that that database can handle spectra as it handles all other sorts of measurements. So what you can see here is that's the response of the database for one specific samples. The blue frame here is basically the metadata on the site ID, that sort of stuff, or the location. The red frame is your wet chemistry. So in this case, we have clay, we have carbon, organic carbon, etc. But then what we've managed to add is directly pointed to either visible near infrared or mid infrared spectrum. That makes the analyst life a lot easier. So this is a little bit of R code. I swear this is last bit of code. But what it shows is basically in sort of 1, 2, 3, 4, 5 instructions, you can directly pull the entire spectral library and build a model. Right. So the data can go straight from the very latest version of the database into modeling, and we can update those models as we go. So I'll leave you with that. So there's always a trade-off between accuracy and cost when it comes to picking between the different spectroscopy methods. Making method operational certainly gave us a lot of new challenges, which is kind of unglamorous from a science perspective, but are very necessary. And finally, in terms of standards, this is an area where there's not necessarily a lot around, but it's an emerging topic. So as an example, we are part of a ring test where different samples from the US have been sent all over the world in different soil spectroscopy labs, so that we can compare the performance of scanning basically the same soils across a variety of instruments. And that's me. Thank you very much.